Hello guys and welcome back to the Maths and Physics vlog. Today we're going to go over Coulomb force, charges, charge density and electric field. So, what is Coulomb's force? Well, Coulomb law is the most fundamental law in electrostatics and it describes the force between two charged bodies at rest. So it's the force felt on one charge, Q1 for example, given experienced under Q2, and it's given by this equation here. As you can see, this is the force felt on charge Q2, as that's the one out to the front of the equation, due to the electric field created by charge Q1. And these two charges are separated by the distance R2 minus R1, and this is in absolute value at the bottom because it wants to be the positive, because then it gives you, to the right equation, the R2 minus R1 over the absolute value of R2 minus R1 gives you the distance, the actual vector direction. So we can tell that the force is felt on the charge Q2 from Q1 electric field, and the vector R2 minus R1 tells us that which way the force is pointing, and it's pointing towards Q2. And then in order to get the charge felt on Q1 by the electric field produced by Q2, we just swap the ones and the twos, so then you get the equation right at the bottom of the screen there. So, some remarks on this Coulomb's law. The force is directed along a straight line connecting two charges. As we know, that is the fastest way to get to point A and B, is to go through a straight line. And if the charges are similar sign, then they are repulsed. But if they are opposite signs, then they are attracted to one another. And we know that the force from Newton is equal and opposite, and so therefore the force 1, 2 is equal to the minus the force of 2, 1. Force felt between them. So now we need to get into electric fields, because we said in the first part about Coulomb's law about it being created by the electric field of the second charge. So we know that Coulomb's law is the change experience of force of electric field created by another charge. So then how do we calculate the electric field produced by a charge? Well, we use the equation here. And notice how it's kind of a similar equation, apart from we've lost one of the charges, and now instead of R2 minus R1, we have R minus R0. And this is so we have a charge Q located at R0. So that means that R is our location in space where we want to test the electric field. That's why it's E in the brackets R. It's the electric field due to R. And then we have minus R0 to go, that's where the charge is in space. Now sometimes you'll have, let's say in a question, you'll have the charge at the origin, which just means that R0 will be at 0, will be 0, and so you just have R over R cubed. So that is the electric field equation of a point charge in space. So now if we have multiple charges, there has to be a better way of doing it. So we get a sum here, which if you know sums, it makes perfect sense, as you have the Qi, multiple different charges from 1 to n, and then you also have their distances located. So what if we have loads of charges, like doing a sum from 1 to 1,000, you can sometimes do it, but then if it gets to a million, it's like there's so many charges in space that it will get out of hand. So there must be a better way with dealing with lots of charges. And then that's where we learn about charge density. So let's say we have a line, a line of wire carrying some current. We know there's a lot of charges in there. So in order to get the charge of the wire, we can split the line of wire into little segments of delta x, and each of these segments have delta q charge. And we say that line charge density, lambda, is equal to the change in charge over the change in distance. Now if we set the size of the segments, the delta x, really small, then we can get an equation that looks like dq equals lambda dx. And then as it's in differential form, we know that in order to get total charge, we just have to integrate both sides, and so we get q equals the integral over the area of lambda dx. We can also do the same thing for surface charge density, where we get dq equals sigma ds, or over volume charge density, where we get rho, delta q equals rho over delta tau. And here s is our area and tau is our volume vectors. So as we mentioned, this integral, we just have to integrate them both to get the total charge in the surface or in the volume. Let's say that our surface charge, line charge density, surface charge density, or volume charge density is uniform. That means we can take it out of the integral, so we can get q equals lambda integral over dx. That's only if the surface charge density or the charge density of whatever we are testing is uniform. So in order to then put this back into Coulomb's law and put it back into the electric field, they are on the right here. So we can apply this in order to evaluate electric fields over a large surface of different large surfaces of different charges and loads of different charges. And notice how the prime symbol has been used as we are calculating the electric field at position r with the elements all at different positions r primes. So this means that if we have, let's take the top example, the top one for example, we have the electric field at r due to the multiple different charges at r prime. I hope this makes sense. Thank you guys for watching. Make sure you like, subscribe and comment any videos you'd like to see, and I'll see you guys in the next video. Goodbye.